Okay, part 3 of the STAV Unit 3 and 4 2021 trial examination. This is questions 10 to 18, the last section. Okay, question 10, let's get straight into it. This is about transformers. Excuse me. This is a very typical diagram that they give you. There's a generator at one end, something that uses electricity at the other end, a couple of transformers, and between the two transformers there are a lot of transmission wires, and they typically give you a resistance in this middle section, or they typically give you a power loss in this middle section. Right? And the transformers are nearly always ideal. I don't think I've ever seen a non-ideal transformer. Excuse me. Okay, so let's have a look at this diagram. You can sort of read that, but I would go the diagram first and then read the rest. So generator makes 300 megawatts. That's 300 million watts. Now you have to watch the units on this one particularly carefully. At 20,000 volts, kilovolts is 1,000 volts. And this is 1.2 thousand volts. This is 1,200 volts on this side of the first transformer. 60,000 volts on this side. All right. Excuse me. In fact, that's not 1,200 volts. That's 1.2 by 10 to the 3. That's 1.2 million volts. That's 1.2 thousand volts. So be careful about that. They're trying to fool you with a few units here. Okay. What is the size of the current in the transmission lines? That's in the middle. Okay, what do we have to work with here? So every transformer conserves power from each side. However, the ratio of voltage and current changes. So here's what actually happens. VI equals VI, right? Primary, secondary. You've seen this before. And a step up transformer, which this is, because that is 20,000 volts and that's 1.2 million volts. The voltage goes up and the current goes down by the same factor. All right. So at the moment, we know that the voltage times the current on this side equals 300 megawatts. So the voltage times the current on the other side is also going to equal 300 megawatts. That's what I've got over here. All right. So on this side of transformer 1, on the secondary side of transformer 1, you know that the power is 300 megawatts. You know that the voltage is that many volts, and you just use P equals VI to find out what the I is. But the power, the voltage, and the current have to be all at the same position. Right? They have to be the same position. They all have to be RMS and peak, or all peak to peak as well. So as long as you've got everything matching both where it is and what it is, you're going to get this right. The formulas themselves are pretty straightforward. Okay, so part B is asking how much resistance is in these transmission wires, and they've told you the power loss. From one end to the other end of these transmission wires, it loses 250,000 watts of power. All right. You know that the current stays the same. The way that they lose power is they lose voltage. Right? I stays the same, voltage goes down. So formula over here for power loss is P equals I squared R. We're trying to find the R. Power is 250,000, I is 250. We just found that out in part A. Do the math, 4 ohms. And that makes part C pretty easy. The voltage loss, same question. How much voltage is lost from there to there? Same section. So for that section, we know that the voltage loss is IR, V equals IR. We now know what the R is, 4 ohms. We know what the I is, 250. So it loses 1,000 volts. Now, the question didn't actually ask for the voltage lost. It asked for what the primary voltage at transformer 2 is. So having lost 1,000 volts and having started with 1.2 million, sorry, with 1,200,000 watts, you need to go that minus that, and you get 1,199,000 volts. That's still a lot of volts. Okay, the last one isn't quite so straightforward. This is part D. With all the rest of the equipment unchanged, the output of the generator, in fact, I'm just going to lower this so we can still see the diagram. With all the equipment left unchanged, so same everything, the output of the generator is doubled to 600 megawatts while keeping the voltage at the same level. By what factor will the power loss in the transmission lines increase? All right. So same voltage, same power, power equals VI, so the current must have doubled. The way that they would double the power would be to double the current, given that they didn't do anything to the voltage. Right. So if the current is doubled over here, then it's going through the same transformer. It's going to be doubled over here. It's going to be doubled on the transmission lines. Okay. So if the I is doubled, right, given that it's squared, 2 squared is 4, so the power loss is going to be quadrupled. And that's all you have to do. Just basically spell it out like this. This, by the way, this shorthand is still full marks. Right, question 11. Something completely different. A spaceship is traveling at 0.94 C, passing by a stationary observing station. That's what I said. Part A, what was the length of the spaceship as measured by the scientists at the observing station? If the length of the ship was known to be 75 meters when measured in a stationary frame of reference. So people on board the ship would measure it to be 75 meters long. How long does it look to a stationary observer as it flashes past? So firstly, you have to find the Lorentz factor. I'm assuming you know how to do that. I'm not going to waste your time with this. Lorentz factor is 2.93. You put in 0.94 C as the V in that formula and 1 for C in that formula, and you're going to get that. All right. And then you do this. The proper length is the length pardon me, let me start that sentence again. The proper length is the length of this spaceship as determined by someone who's in the same type reference frame as the spaceship. In other words, somebody traveling along with it. Or how long you would measure it when it was stationary. Right, so there's the proper length. The improper length is this. So 75 meters divided by 2.93, and it would appear to be 25.6 meters. You know the answer has to be less than 75. The only way you're going to get this wrong is you're going to mix those up, or you're going to mix the formula up. Some people get the formula wrong. I don't know why. You've got a cheat sheet, put it on. But there are some people who go L equals, like that. Okay. But most people who get this one wrong literally just put the numbers around the wrong way. However, you should realize that the answer has to be less because it's not called length extension. It's called length contraction. Right? So given the normal length, right, the weird length should be shorter, not longer, every single time. Okay. Part B, same sort of deal. An astronaut on the spaceship boils an egg in 2 minutes. According to the scientist observers at the stationary observing station, how long was the egg boiled? It was boiled for 5.86 minutes. That is because of time dilation. Right? Time literally clocks spin and tick slower on the spaceship. So 2 minutes on the spaceship, right, on a slow turning clock. Back home, the clocks go at the proper speed. They're going to go through more minutes. They're going to go through 5 minutes at the same time as 2 minutes on the spaceship happens. So according to observers on Earth, we look at their clocks and see that their clocks are going slowly, and that's why, and that's why we know that the people on the spaceship are only measuring 2 minutes of time for their egg to boil, while we measure 5.86 on our proper fast working watches. Right? From the perspective, from the perspective of the ship, the time is ticking away perfectly, right? But things are happening a little bit faster. So a 5.86 minute boil only happens in 2 minutes, so the eggs just seem to cook faster. And also the distances out the window seem to be shorter. Question 12, we've seen this formula a lot in the last couple of exams that we've done. All right, this should be a pretty straightforward one. It basically says a satellite is taking an elliptical path around Earth. It's going to get closer and closer and closer. At this particular point, point C, it is 10 Earth radiuses away from Earth. And the question says, calculate the magnitude of the gravitational force acting on the satellite at point C due to the Earth. Okay, so you have to calculate the right radius. It just tells you that it's 10 Earth radiuses. And so you've got to figure out what that is. One Earth radius is 6.37 by 10 to the 6 meters, so that's 10 of them, right? Pardon me. Now, by the way, there are two different units for this: meters per second squared or newtons per kilogram. And that is because a newton, F equals ma, right? Therefore, a newton equals a kilogram times meters per second squared, right? Pardon me. So that formula, that unit, can also be written newtons divided by kilograms, if you sort of put that down there on the other side of the equal sign, right? That and that literally stand for the same unit. That's where they've got each of those from. So it's both an acceleration and it's a force that's on each kilogram of this, in this case, the satellite. Okay, part B. There's a graph coming. You know how I feel about graphs. Let's get this right. Okay. The following graph represents the gravitational field of the Earth as a function of the distance of the satellite from Earth. Stop and look at the graph. All right, let's have a look. Gravitational field strength, so that's this number, and it's in the same units, which is great. It's not in kilonewtons per kilogram or something, so it's very simple. Good. Distance from the Earth multiplied by Earth radiuses. That is the Earth's radius. So that's 1 Earth radius, 2 Earth radius, 3 Earth radius. All right. So that matches what they showed on the diagram. Handy. Okay. They've labeled point A. They've labeled point B. There must be a reason for that. Okay. Use the graph above to estimate the increase in kinetic energy of the satellite as it travels from point B to point A. Okay, so point B is further away from Earth to point A, so it's literally falling towards Earth. So it is going to speed up. So there will be an increase in kinetic energy. And the increase in kinetic energy is the same as the decrease in gravitational energy. So have a look at this. That comes to the area under the graph, right? Graph tips, two of them. The change in the vertical of any graph, this applies to any graph at all. The change in the vertical divided by the change in the horizontal equals the gradient. You've known that for a few years now. The change in the vertical multiplied by the change in the horizontal equals the area under the graph, right? So we want to go from point B to point A. There you go. So we're trying to figure out what that area under the graph is. So back to the question. Like I said, change in kinetic energy, the increase in kinetic energy is going to be the loss in gravitational potential energy. Gravitational potential energy is mgh, right? And that multiplied by that is this, because that's delta H and that's delta G, okay? So we need to get the area under the graph and multiply it by 1400 kilograms, because that was the M, that was the mass of the satellite. That's what we're doing down here. Now, area under the graph, how do you do it in VCE? The answer scheme to this document, to this particular exam, gets this a little bit wrong. The VCE is happy for you to do this, to say that's a full square, that's more than half, and that's more than half. Right, so that's 3. Right? In fact, that's about half, and that's about another half. Right, so 1, 2, 3. Okay, you can be that rough. Right? This is not a calculus question. This is not maths. It is a physics exam, so they don't want you to muck around and spend 10 minutes trying to figure out exactly how much area is under a curved line. Very, very roughly, that's fine. Okay, so you can say the area under the graph is 3 squares, and they will agree with you. They'll say fine with that. Someone else will say 2.5. They'll be fine with that as well. Right? I think the answering scheme said 2.75. So the kinetic gain is 3 squares times the value of each one of these squares, and one of these squares is that times 1, right? 6.37 by 10 to the 6 across and 1 up, so that's what it comes to. right? So those multiplied together, that's the delta G, delta H bit. And that's the M. So it's mgh. That's the kinetic energy gain. 2.68 by 10 to the 10 joules. That's a lot of explaining for something that's actually a fairly simple process, but I thought I'd just give it to you properly. All right. Question 13 starts off pretty damn easy. James is seated in his office chair. James has a mass of 85 kilograms. The chair has a mass of 12. What's the force of James and the chair on the floor? Well, you add up the M's and you multiply that by 9.8. Right? 85 plus 12 is 97. That's mg multiplied by 9.8, 950.6 newtons down. Say down. It's a vector. Oh, especially because they gave you a box for magnitude and the box for direction. All right, part B. What's the force of the chair on James? Right. The force of the chair on James equals the force of James on the chair, right? Equal and opposite reactions. Okay. So the force of James on the chair is just James's mass. So it's not this. It's just James's mass pushing down on the chair. Okay. So that's him down, but the chair is forcing him that much up. Easy. Okay. Part C. Brian and Tony are discussing Newton's laws. Brian says that the force of James on the chair and the chair pushing back on James is an example of Newton's third law. Tony disagrees. Right? Who's correct? Brian's correct. It is an example of Newton's third law. I just want to sort of show you how to work Newton's third law, because this comes up a lot. Newton's third law tends to be the one that they pick on in these exams more often. You don't normally get examples of show why this is an example of Newton's first law. Third law is always the one people pick on, because a lot of smart people get this one wrong. Right? Equal and opposite. And everything about it is opposite. So James is forcing the chair down. Right? The opposite of that is the chair forcing James up. James and the chair are opposites. The chair and James are opposites. Down and up are opposites. Everything about the phrase is opposite. Okay. Newton's third law, the pairs of forces that happen are always two different things forcing each other. So if the action force, it's all action-reaction, if the action force is James forcing a chair, the reaction force won't be James forcing something else. All right? It's going to be something forcing James. All right? Everything about the sentence that you write down here is the very opposite. James, chair, chair, James, down, up. That's it. 14, the obligatory speaker question. Happens all the time. I think about every second physics exam I've ever seen has got one of these, a speaker question. If it's not speakers, it's light going through some slits. Okay, but you're going to get a diffraction question for sure. Two identical speakers A and B are placed in a position as shown. This person is standing equidistant from the speakers at the moment, and then over here they move to a spot where there's a path difference. Right? That's essentially what that's saying. You need to know that the speakers are producing the same 680 hertz sound. So we've got the frequency. The speed of sound is 340. So we need to know that. Number one, calculate the wavelength of the sound. Easy. V equals F lambda. Got that formula. Wavelength is V on lambda. Ta-da! Easy. Half a meter. Now this next question is unnecessarily complex, right? For what is actually a simple question. You've got like 5 lines of stuff to read, so let's get through this, right? So basically it says, the man stands there and hears a loud amount of sound, because obviously they're at constructive interference. We know that he's standing at the central bright, literally, or the sound version of the central bright, which I guess is the central loud, right? And then he moves across and he gets to here where there's a path difference. He gets to 6 meters away from A and 5.25 meters away from B, and this tells you that at that point he experiences a quieter area. And the question says, how many quiet regions, including the one he's now standing in, has he experienced since he has moved from there to there? That's what we're asking. So he's in one of the quiet areas, he's in one of the areas of destructive interference, but he's in the first one or the second one or the third one, etc. Okay. The path difference at that second location is 0.75 meters, which is 1.5 times the wavelength. Wavelength is 5 meters, right? 6 minus 5.25 is 0.75. That's 1.5 of those, right? Quiet regions are caused by destructive interference happening at path differences that end in half a wavelength. It's either half a wavelength, 1.5, 2.5, 3.5, etc. Right? The first one is at half a wavelength. So he's already gone through that. He is standing at the second one, 1.5 wavelengths. So at this point, he has walked through the point at which the path difference is half a wavelength. Therefore, he has gone through 2 quiet regions, including the one he's standing at. All right. So that is a little bit more wordy than you need to put it on there in the 4 lines that they gave it to you. But that's the proper explanation for you. Okay. Okay, question 15. Just let me center that for you again. Perfect. Right. Standing waves are formed on a string of length 6 meters that is fixed at ends A and B, right? Excuse me. The speed of the waves along the string, this is not the speed of sound. This is the speed of the waves along the string, is 240 meters per second. The string is shown in the diagram below. Okay. Calculate the wavelength of the third lowest frequency resonance. Now I've just drawn this down here. That's the lowest frequency. The lowest frequency is the biggest wave, right? Biggest wave, smaller frequency. And as long as it's fixed at point A and point B, it's fixed there. So they have to be nodes. Nodes there, nodes there, nodes there. They have to be points on which a standing wave basically doesn't move up or doesn't move down, right? And the biggest one of those that you can fit, and therefore the largest wavelength and the lowest frequency, is the wave that only fits half of it along the 6 meter length. So that wavelength is going to be 12 meters. The next one up, so the next one down, I guess, if we're talking about shorter wavelengths, is the one where it's exactly 1 wave, right? And then exactly 1.5 waves. Now there's a formula. You can either draw this and work it out, right? Or there's a formula that does it for you up here automatically. Right? There's another formula for open tubes as well. That's the other way to make, one of the other ways to make sound. Excuse me. So you can either sort of nut it out like this, realizing that that must be the third lowest frequency because it's the third biggest wave. And how big is 1 wave? If that's 6 meters, then it's got to be 2, 4, 6. So 1 full wave is 4 meters. The formula will get it for you as well, okay? N is 3 because you're looking for the third wave, right? And the length of the string was 6 meters. In this case, 2 times 6 divided by 3 is 4. So you're going to get the same answer either way. Now, part B, it says calculate the frequency of the third lowest frequency resonance. Well, this is from V equals F lambda. I've just juggled it around. We've got the velocity. They told us that they were traveling along the string at 240. We've now got the wavelength, 60 hertz. Right? So that's pretty easy. Now, part C literally asks you to draw it. Right? And they've given you another wave there, and you have to draw this. And again, you don't have to be artistic about it. Right? You basically just have to make sure that you know that, especially because you've now calculated that the wavelength is 4 meters, you know that that's 6 meters. So just divide it by 3 roughly. So that's 2, 4, 6, right? And you have to have an entire wave in the 4. So just freehand it and then just do the rest, right? Easy. Doesn't have to be up first. You go down, up, down if you want. That's okay. But that's how to do these things. That really should be pretty, free marks for you guys by now. Question 16. I just want to straighten that a little bit. Okay. Right. Double slit experiment. I'll let you read it. You can pause and read this yourself if you want, as with everything. Double slit experiment. There's D. There's L. This is the pattern of bright and dull areas. P0 is the central bright. Okay. They've given us some figures here. The power output of the laser is 5 milliwatts. That's a small m. Don't go megawatts. That's a small m. That's milli. All right. The laser is a wavelength of 584 nanometers. So once again, be good at converting that to meters. Pardon me. All right. And we understand what's going on here. And delta x, of course, is the distance between adjacent bright spots. Calculate the number of photons leaving the laser each second. Here's how to do it. The energy of one photon is easy to get. E equals hf. We've done that a lot. F equals c or lambda, right? Because c is the velocity. That's the same as this one here. F equals v on lambda. For the special case of light waves, the v is c, the speed of light. Okay. So energy equals hc on lambda, and put the numbers in, and it comes to that. Right? So that's the energy of one photon. Right? Now, power is how much energy you're getting per second. Now this said 5 milliwatts. So in 1 second, we're getting enough of those coming by to add up to 5 milliwatts. Right? So here's how to do it. How many photons do you need to generate 5 milliwatts? You need 5 milliwatts divided by how much energy is in one of them. And it comes to 1.47 by 10 to the 16. So every second the laser is putting out 1.47 by 10 to the 16 photons of light. That's how to suss that one out. Well, let's just get the next page here. Question B, 16B. What is the path difference in nanometers of the sources S1 and S2 to the central maximum? To the central maximum, it's got to be 0, right? No path difference there at all. Okay, so it's just 0. Even in nanometers, it happens to be 0. I like how they said, oh, do it in nanometers. So don't be fooled by little things like that. Again, that's the sort of thing that someone goes, oh my God, it has to be in nanometers. It must be a number. I've done it wrong. No, you haven't. Trust yourself. Path difference is 0. There's no trick there. The trick was this. Okay, part C. What is the path difference in nanometers? You're going to get an answer for this one. For the sources S1 and S2 to the third minimum. All right, minimums. On the screen below the central maximum. Okay, central maximum. First minimum, second minimum, third minimum. Let me get this out of the way for a second. At the first minimum, the path difference is half a wavelength, 1 wavelength, 1.5, 2, 2.5. So it's 2.5 wavelengths there. And did they say in meters or did they say in wavelengths? Sometimes they say wavelengths. Oh no, in nanometers. All right. So it's 2.5 times the wavelength. And the wavelength is 584 nanometers. They gave you that. So you just have to go 2.5 times 584, which is what I've done down here. 1,460 nanometers would be the path difference there. So that's B. Pardon me, C. And now it's D. Explain how this experiment is used to support the wave model of light. All right. We've seen enough of these questions before. Here's a pretty decent way to start. Now what I would write is in grey and my instructions for you are in green. Right? So start at the observation. Right? There, you're linking the experiment and the wave model of light. So start there and get to there. Right? The experiment showed you bright and dark lines on a wall, so talk about that. The bright and dark lines produced in the experiment are the result of, now you're talking to the physics, right? Are the result of constructive and destructive interference. And now you've got to get to the wave model. Right? Make sure to quote what the question is about. It's about the wave model of light, which are only caused by waves, indicating that light is a wave. And that's the wave model of light. So the grey stuff is one sentence that literally does those 3 green bits. That's a fairly short way to do it. Okay, part E, last one. The laser is changed to another laser with 670 nanometer waves. Everything else about the experimental setup is the same. Describe how this change of wavelength changes the pattern on the screen. Again, don't say anything else. Just worry about the pattern on the screen. The pattern on the screen is dictated by delta X. Okay, so yeah, go straight to the formula. Right? If the wavelength is bigger, and 670 is bigger than 584, then that's going to be bigger. Okay, if the wavelength is increased, that increases. The pattern on the screen will therefore be more widely spaced. You can't stop there. That's just the maths. Right? It is saying, how does it change the pattern on the screen? Right? That'll get you halfway. It's 2 marks. I think that'll get you 1 mark if you do that. Right? So you're just going to have to say, therefore, the pattern on the screen will be more widely spaced. It'll be spread out. There'll be bigger gaps between the bright areas. however you want to say it, but actually finish it off with that little sentence there. And again, it doesn't have to be huge. That's still 3 lines. That's all they gave you. Should be plenty. All right. Okay, question 17. This is one of those very nasty things that are right at the end of an exam. There are 2 questions left. You've got 20 minutes left, and then you see this enormous thing here. Right. So there's 6 lines to read. There's a difficult diagram to look at. There's a table of figures, and then you turn the page over and you see what's the question, and you've got to draw a graph. So there's a lot to take in here. Right. It's actually a pretty easy question, right? But there's a fair bit to take in. So either pause it and have a read yourself, or I'm just going to give you the summary here. Okay, I'm going to assume you've read it. Okay, we basically have the photoelectric effect happening here. There's light you can put different filters here to make sure that only one wavelength of light gets there, only one frequency. So you can control the frequency of light that hits the photocell. That induces a current, which can be stopped by the stopping voltage. Right, reasonably simple setup. They haven't given you any information here that's quantitative. They haven't given you any figures, any numbers. They have given you some down here. They changed the frequency, so that's the independent variable. And that, of course, changed the stopping voltage, as it would, because higher frequency means higher energy per photon, and therefore a higher maximum kinetic energy that has to be stopped by more voltage. Okay, that we understand. So, question A. On the following axes, plot the maximum kinetic energies of the y-axis on the y-axis against frequency on the x-axis. On the graph, draw a line of best fit for these plotted points. Now, a few things I want to tell you about this. I'm just going to dial up the light a little. Just hang on a second. Just realized that was getting a bit dull on the screen. All right. So they've done us a couple of favors here. Firstly, the units on the table are the same as the units on the graph. And this is one of the things to make sure of, right? These are some tips here. Right? Check that the table's units match the graph's units, because occasionally they don't. And you have to literally convert everything to the right unit before you plot the points. And that is a pain in the neck, and it's another 3 or 4 minutes that you really don't want to spend. Luckily, they didn't get you to do that this time. Everything's fine. Let's just get the table and the graph on the same picture, on the same page. There you go. All right. So that's frequency. That's frequency. Times 10 to the 14 times 10 to the 14. Perfect. Stopping voltage, good. All right. Electron volts, they're the same number. They are different units, but they're numerically the same in this particular case. Okay. Make your plotted points noticeable, right? One of the things that some of you in this class in particular that I'm talking to do is you do this in pencil, and you do tiny little dots, and then you draw over it with your line of best fit, and you can't see where the dots are. You must show the plotted points to get the full marks, right? One of these 4 marks is going to be for plotting the points correctly. If they can't see the dots, they can't give you the mark. So don't do these tiny little pen or pencil dots, right? Do that. Make it fat, make it big, right? Make it stick out on the sides of the line of best fit. It should end up looking like that, right? Okay, so make it obvious. Now, I'm not going to draw it, right? You've got the answers in front of you. You've seen the answers. You can have a look at it, look at the final thing yourself. So I'm not going to waste your time by having you sit there watching me draw a graph. You know what it looks like. You've got the response there. Okay. So part B, after having drawn it, it says, using your line of best fit, determine the threshold frequency for cesium. The threshold frequency is the x-intercept of this one. So you just basically have to say that, because it says using your line of best fit. Right? In fact, in this particular case, they haven't even given you a line to say anything. They just want you to give the number. Usually in the VCE exams, if they say using your line of best fit, you have to show some evidence that you've used it, right? That you've done that. You have to say, from the line of best fit, you know, the x-intercept, as you can see on the graph, equals blah, 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 right? And then say it. Right? In this case, they're not bothering. They just want your number. Okay, so measure the x-intercept. It looks like about 4.4 by 10 to the 14 hertz. They're going to be pretty generous with it, right? If you say 4.6, they're going to give it to you. If you say 4.2, they're going to give it to you. You have to be reasonably good at reading a graph, but they're going to give you a bit of wiggle room there. All right, part C, which is over the page, I believe. Yep. Use the graph and a calculation. So once again, you have to use the graph and you have to use a calculation, or they can't give you full marks. Do what the question says. To determine a value for the work function of cesium. Okay, the work function is the y-intercept. Pardon me, let me just draw. I mean, this is obviously wrong. I'm not even looking at the numbers here. But if that was the plot, that is the work function. Like on mine, it looks about minus 1.4 there. That is the threshold frequency, and the gradient is Planck's constant. We know there's 3 things about this particular graph. We've seen a dozen of them by now. Right, you have to use the graph and you have to use a calculation. So the answer, again, I would do what I've done here in grey. The y-intercept of the graph is negative 1.8, so I've clearly got my line wrong, right? And therefore, 1.8 times 1.6 by 10 to the minus 19, which is the conversion factor between electron volts and joules. They've asked you for the answer in joules, is that. Right, so you've used the graph, you've used a calculation, that's what they mean. All right. D, which I've now drawn all over, excuse me. Use the graph to calculate the experimental value for Planck's constant, that's the gradient, right? You must show your reasoning and working based on evidence from the graph, right? They've even put it in, right? All capitals here. Use the damn graph, right? So give your answer in EV seconds. Now that tells you, excuse me, you've got to calculate the gradient. You know how to do that. You just pick 2 points that are on the line and go delta y divided by delta x. You know how to do a gradient, right? The answer is going to come out in EV seconds, not Joule seconds. Right? So it should be close to the value of 4.14 by 10 to the minus 15. It shouldn't be anywhere near the 6.63 by 10 to the minus 34. So it should be close to the value of Planck's constant that is in electron volt seconds. Okay. Pardon me. Last one. E, the intensity of light from the source is doubled, but everything else is kept the same. How would that affect your calculated value of Planck's constant? It wouldn't. Firstly, Planck's constant is constant. Nothing affects Planck's constant, no matter what they changed. It wouldn't affect that. Every graph that has ever been drawn of this particular experiment has the same gradient. It's a damn constant. Okay. And the other reason it doesn't affect it is because the intensity of the light doesn't change anything at all about this, right? It doesn't change the maximum kinetic energy of the electrons either. So, so nothing would have changed at all. All right. And by the way, there is only 1 mark for that. So you just have to write no change. You don't have to give them a reason. Just say it. If it's only 1 mark, you just basically state it. All right. We are up to the last question. Actually, scratch that. We're not quite up to the last question because there's an F for this, just when you thought you were done with it. All right. What evidence from this experiment supports the particle model from light? And again, start there and get to there, right? Evidence. Excuse me. The evidence is in the table that it has a threshold frequency, and it's been graphed as well, right? There are some frequencies, no matter how bright the light is, that don't make the photoelectric effect happen, right? And that is ample evidence that light must exist as photons. It must exist as discrete little bundles of energy, and one of those discrete bundles hits 1 electron, and it's either got enough energy to take it out or it doesn't. Right? That it's not a continual wave that can sort of add up the energy to an electron and give it more and more and more and more until it's got enough energy. All right, that's the wave model. Okay, the fact that it has a threshold frequency and that the fact that the intensity of the light does not change a damn thing is what led to the idea that light exists as discrete bundles called photons. All right, so you just have to make those connections. Now, we're up to question 18, the last question. And this one is easier than 17. This one's a pretty easy question when you look at it. Okay, following is a diagram representing the energy levels for a sodium atom. Fair enough. Look at the diagram. N equals 1, N equals 2. Electron volts, not joules. Good, this is the ground state, and that's ionization. 10 seconds looking at the diagram. A, calculate the frequency of a photon that is created by electron transitioning from N equals 4 to N equals 2. Okay, so it goes down from 4 to 2. Does that. It will release the difference between that much energy and that much energy. So this is what I've done. 3.61 minus 2.1 is 1.51 electron volts. So whatever photon came out, it's got 1.51 electron volts of energy. Right? E equals HF. So I'm gonna juggle that around and get the F. Okay. And because this is an electron volts, that's the version of Planck's constant that you use. Right? Don't do the wrong one. Ends up being 3.65 by 10 to the 14 hertz. Most frequencies, in fact, all frequencies of visible light are in the 10 to the 14 hertz, right? If you had put the wrong value of Planck's constants there, you'd get something like 10 to the 27 or something, right? That's a gamma ray, right? Okay, part B. On the energy level diagram above, indicate with an arrow the electron, so don't draw that by accident, indicate with an arrow the electron transition where a 1.65 electron volt photon has to be emitted. You just have to figure out which two of these have got a gap between them, which two of these numbers have got a 1.65 electron volt gap between them, and it seems to be, and it's that one to that one, right? 3.75 minus 1.65 is 2.1. So that is the answer. And by the way, if you were a nutcase like me and you've already drawn an arrow on there just in your working for part A, just say this is part B, like that. Right? Make it clear and you'll be fine. Part C, calculate and list the various photon energies that could be emitted by the decay of an electron initially in the N equals 3 state. So we're starting there. There are 3 of them. Right, there's going straight down to the bottom, there's going there, and then from there, having landed there, there's going down to there. Right, so they're the 3. And all you have to do is this, N equals 3 to 2, 109, 3 to 1, 2 to 1. Okay, show the one minus the other, right? It said show, if it says show your working in particular, no, it didn't show your working, so you're probably going to get away with just doing this. All right. If it doesn't say show you're working and it's only out of 2 marks and you've got 3 numbers, that is probably fine. In fact, it's certainly going to be fine in the VCE, because the VCE reasons that you can't possibly have guessed all 3 of those right if you didn't know how to do the question. If it says show you're working, or if it's out of 3 marks or 4 marks and they've given you some lines, then they expect you to show how you did it somehow, right? With at least one example. If there are 3 repetitive things that you're doing the same thing all the time, you can show one example and then just write similarly the answers to the other 2 are, right? And you don't have to do the working 3 times. Just do the working once and say, hey, this is how I did all the other ones, and give the answers. All right, nearly done. (18D). State the difference in appearance between an absorption spectrum and an emission spectrum. Now, this is another one of those cases where you can really get this wrong by writing too much. It's only worth 2 marks. You should finish your answer about there, honestly. Right? It should be a 4-line mark at the most. Excuse me, 4-line answer at the most. You are only stating, you're not explaining. It says just tell us how it looks different. And you're only stating the difference in the appearance. You're saying, how do they look different? You're not saying why. You're not saying what causes it. You're not saying what its significance is. You're not sort of talking about the wave model of light or anything like that. You are just saying, you know, an emission spectrum looks like this and an absorption spectrum looks like that. That is literally what this question is asking. There is a classic This is a classic question where people are going to write too much and start contradicting themselves, or they're just going to do a brain dump. And if you just do a brain dump, that tells the person who's marking your exam that you didn't know which part of your brain dump was the actual answer. So you just say everything that you want to say. You just say everything you know about this about this particular subject and hope for the best. Don't do that. You have to answer the question exactly. State the appearance difference. That is it. So here's the answer. Don't write too much until I've done this. An absorption spectrum is a continuous spectrum of visible light with some dark lines where light is missing. Right? You don't even have to say why the light is missing. It's just the appearance. An emission spectrum is entirely black, but for a few lines of light that are there. That is it. That's the answer. No explanation, no theory, no nothing. That is it. Right? 2 marks. Perfect. Okay, last bit. Calculate the de Broglie wavelength of an electron with 1.65 electron volts of kinetic energy. Okay, de Broglie wavelength has got momentum in it. You've got to get momentum. Here's how you go from kinetic energy to momentum. We've seen this one before. All right. You had the kinetic energy, 1.65 electron volts. You have to convert that to joules. This one only works in joules. Right? So that's what I've done. That's why we've got like 10 to the minus 25s going on here, right? Because I've converted the electron volts to joules first. And then once you've got that, put that answer on the bottom of this. Planck's constant on the top. Again, the joules version of Planck's constant, not the electron volts one. And that is the final answer for this test. Thank you very much for putting up with me and getting to the end with me. I'll see you at school.